Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll begin a new unit called linear programming. So we'll basically be trying to solve certain types of problems, which will be called linear programming problems. So what exactly is a linear programming problem? Well, it is a problem in which you have to basically optimize a variable. Optimize could be either maximize or minimize. So it's a problem in which you have to maximize or minimize, sometimes often called optimize. So we have to maximize or minimize a function. Now you can maximize minimize functions by differentiation, but that's for one variable. This is a function of many variables subject to some constraint. So a simple example, we'll look at the meaning of this problem in a minute, but right now let me just write the problem in a mathematical form. Let's say you want to maximize the function z of xy, which is equal to 5x plus 3y. Now of course, by default the maximum value would be infinity when x and y are both infinity, but we are given some constraint. So this is the function, but we cannot take x and y both to be infinity because there is some constraints. The constraints may be, for example, 3x plus 5y has to be less than or equal to 15. So for example, these two, we cannot take x and y to be infinity. Another constraint would be 5x plus 2y less than or equal to 0. And finally, for our course, we will always assume two extra constraints, x greater than or equal to 0 and y greater than or equal to 0. So for the scope of this course, we will assume that all the variables are positive or 0. They are non-negative. So if we have to maximize this function subject to these constraints, then we'll have to do a little bit of calculation, because we can take x and y both to be 0, then this function is 0. We can take x and y to be some numbers, there's a range, there's an upper limit based on this, so we cannot take them to be very large numbers, but we have to maximize this function based on these four constraints. So we'll see how to solve these types of problems in a second. Right now we just need to understand that this is a linear programming problem. If this relation inequality was not of a linear nature, let's say we had x squared, then this would not have been a linear programming problem, and that is beyond the scope of our course. So for us, all of these constraints will be purely linear, and we will need to maximize or minimize a function. So before solving or looking at an example, let's just first define a few terms which we'll use regularly. So we'll start with a type of problem that is generally useful in terms of linear programming. So let's say somebody has a shop of tables and chairs, and they need to buy some tables and chairs. So they need to invest some money to buy some tables and chairs, and then they're going to sell those tables and chairs for some profit. Let's say a table costs rupees 2500 and ends up making a profit of rupees 250, and a chair costs rupees 500 and makes a profit of rupees 75. Now the person who owns the shop has a total amount of 50,000 rupees, from which they can buy either tables or chairs. Now if they choose to buy only tables, let's say, then you have 2500 tables, 50,000 rupees, you'll be able to buy 20 tables. 20 tables, 250 rupees per table, gives you a profit of rupees 5,000. Suppose you only bought chairs, then 500 rupees for a chair means you can buy 100 chairs, and 100 chairs would give you a profit of 7,500. Right. Now let's add one more constraint to that. One constraint is just 50,000 rupees. The second constraint is the man can only have 60 units in the basement, let's say. So there is only storage space for 60 units. That means you cannot buy 100 chairs. You can only either buy 60 chairs or 60 tables, or a total of 60 things. So instead, if you buy 60 chairs, your total profit will be 60 into 75, which will come out to be rupees 4500. And from the rest of the money you could buy tables, and that would add to the profit, right? So the goal of a linear programming model is to find out what combination of tables and chairs should I buy so that I get maximum possible profit. So to write this in form of a linear programming model, we would say that the objective function is z, which is equal to 250x plus 75y. What are the variables? X is the number of tables and y is the number of chairs. So we have to maximize this function subject to some constraints. The first constraint is you cannot spend more than 50,000 rupees. So 2500x plus 500y has to be less than equal to 50,000. Right. An easier way to write this is we could just take care of the zeros. I'll not do it now just for the sake of clarity. The other constraint would be you can only have a total of 60 units, which means x plus y has to be less than equal to 60. And of course there are two obvious constraints, x greater than equal to 0 and y greater than equal to 0. Now if we can cancel this, 100 and 100 and 100 cancel, we are left with 25x plus 5y is equal to 500, or 5x plus y less than equal to 100. Right, this gives me this. So basically this is our linear programming problem. I have to maximize this function subject, let's just remove this for now. I have to maximize this function subject to these four constraints. So before looking at how to do that, let's look at a couple of definitions. The linear programming problem in which you have to find the maximum or minimum value of a function is called an optimal value problem. And the maximum minimum value of this function is called the optimal value. The function itself, which we need to maximize or minimize, is referred to as the objective function. Also, these variables x and y, they are referred to as decision variables. And then obviously these four relations, they would be called constraints. And this whole thing is called an optimization problem. So these are just some of the terms we'll be using again and again. In an optimization problem, which is a type of linear programming problem, we need to find the optimal value, maximum or minimum value. In this case, it would be the maximum. Sometimes, let's say we might need to minimize something, say the cost of goods or something. So this is the optimization problem. This function is the objective function. It is made up of x and y, which are called the decision variables. And we have to subject it to these four equations, which are referred to as constraints. So now let's begin solving it. Now there are many ways to solve linear programming problems, but in our course there is only one way which is in the syllabus, and that is the graphical method. So that's what we'll do. I just write the equations once again. Z, the objective function, was 250x plus 75y. Z denotes the total amount of profit. X is the number of tables, y is the number of chairs. Every table gives me rupees 250 in profit, every chair gives me rupees 75 in profit. Similarly, we are given constraints. The first one turned out to be 5x plus y less than equal to 100. The other is x plus y less than equal to 60. Then you have x greater than equal to 0 and y greater than equal to 0. These are the four constraints. So the first step is to draw all of these constraints on a graph. So my figure will not be completely drawn to scale, so I suggest you draw it yourself and try it. But the important thing is the method of solving the problem. So first is x greater than equal to 0 and y greater than equal to 0. These two directly give me the first quadrant. Means the second, third and fourth quadrant are simply out of the question. So whatever regions these two constraints give me, I'll have to intersect with the first quadrant where x and y both are positive. X plus y less than equal to 60. So what is x plus y equal to 60? This would be 0, 60, and this would be 60, 0, and this line would be x plus y is equal to 60. So x plus y less than 60 would be the whole region to the left of this line. Similarly, we have 5x plus y less than 100. So what is the equation 5x plus y is equal to 100? Well, the best way I choose to look at it is you put each of them 0. So for x plus y less than equal to 60, when x is 0, y is 60 this point. When y is 0, x is 60. Similarly here, when x is 0, y is 100. So we have this point 0, 100. And when y is 0, x is 20. So we have this point 20, 0. Right. So this is the other line. So now what is the region of interest? X plus y has to be less than equal to 60. That is the left part of the first line. 5x plus y less than equal to 100 is the left part of the second line. Right. If you go to any other point, then the values would be greater. And you need to take the first quadrant only. So this is the region in which our variables lie. Right. So we just match all the constraint regions and we find out the common area. So this is the region in which all 4 of these conditions are satisfied. Now we know all these points. This is 0, 0. Let's for a second just figure out this point of intersection. So we have x plus y is equal to 60 and 5x plus y is equal to 100. Subtracting this gives me 4x is equal to 40, x is equal to 10, which gives me y is equal to 50. So this point is 10, 50. So now we found all the points. Let's look at a couple of definitions that go in the graphical solving method as well. Each point in this region is called a feasible point. And this whole region is referred to as feasible region. Right, because this is the region which it basically contains infinite points, and all of those points satisfy all 4 of these conditions. So the whole region is called the feasible region, and any point within this region is called a feasible point. Obviously, any region outside this particular region will be called the infeasible region. Right, and then you have feasible solutions. It should be a I here, sorry. Feasible solutions, which would be a solution satisfying all these constraints, meaning it has to be a point lying within the feasible region. Right. So how do we end up calculating? I mean, the only way to do it is to take all the infinite points, calculate z for all of them, and then figure out which is maximum. Fortunately, there are a few theorems regarding linear programming which are very useful in helping us determine the answer. Now the problem is the theorems are once again beyond the scope of your course. So I will not give a proof of the theorem, I just state the theorem and we are going to use it as is. So I'll just rub the unimportant part. These are just the definitions which I'll use again and again. Yeah. So there are 2 theorems which will be important. The first theorem says that if R is a region, a feasible region, R is a feasible region, and generally it will be a convex polygon. Here we have a quadrilateral, 4 vertices. So whatever it is, it could be a pentagon or something else, a convex polygon. So if R is a feasible region and Z is equal to, let's say, ax plus by is the objective function, and one more constraint, R is bounded. This will be true in most cases. You see, bounded just means it doesn't extend to infinity. So for example, in these 4 conditions, if we removed y is greater than equal to 0, then this line wouldn't have been there and this particular thing would extend all the way to infinity, right here. But we don't want that, so that's why we have 4 constraints. So whenever R is a feasible region and it is bounded, then Z has both a maximum and a minimum value on R. Now this may not be true if it is infinitely large, the region, because then you may not have a particular maximum value. Every value could have a value bigger than that, right? But in this case, Z has both a maximum and minimum value of R. And the most important point of this theory is that each of these occurs at a corner point of R. So once again, we'll not see the proof of this theorem, but what this theorem tells us is this region R is the total feasible region. Right? It is a convex polygon and it is bounded. So this function Z actually has both a maximum and minimum value on R. So a particular combination of x and y will give you the minimum possible profit, and another particular value will give you the maximum possible profit. But the interesting thing is each of these occurs at a corner point, which means the maximum value of Z will either occur at this point or this point or this point or this point. It has to occur at a corner point. Similarly, the minimum value of Z will occur at either this point, this point, this point, or this point. Right. Now, in that case, problem is much more simplified because we can just look at the value of Z at these 4 points. So let's call these A, B, C, and D. So at point A, we have 0, 60, and Z comes out to be 60 into 75, which is 4500. At point B, 10, 50. So we have 2500 plus 50 into 75, which will come out to be, if you try to solve it, 2500 plus 3750 or 6250. At point C, we have 20, 0, so 25 into 250, Z is equal to 5000. And at D, we have 0, 0, so Z is equal to 0. Now from these, the minimum value of Z is equal to 0, so that is the minimum value of the objective function. The maximum value of Z is 6250. So that is the maximum value of this function. That means the man should buy 10 tables and 50 chairs, and that will give him the maximum possible profit. Now we can be rest assured that there's no point inside which gives Z a value greater than this, because that's what the theorem says, that as long as R is bounded, Z has both maximum and minimum values, and both these values lie somewhere on the corner. They'll obviously not be on the same corner, but then since a convex polygon only has a finite number of vertices, you can just calculate the objective function in each vertex and then see which is the best, which is the maximum or which is the minimum. And this whole method of solving is referred to as, I'm going to rub this now, all of this is referred to as the corner point method. So I'll just recap this once briefly for now, and then we'll move on to types of problems, and then we'll do a few examples, because linear programming really as a topic is quite short, but it's only through examples that you really learn. So the corner point method tells us that there are some steps. The first step is find the feasible region. Again, our problem is to maximize or minimize an objective function of more than one variable given some constraints in those variables. So using the constraints, you can easily find the feasible region and then determine all the corner points. Most of the regions you'll be given will be bounded regions, they won't extend to infinity. So you can do it, the best way to do is by solving two equations at the boundaries, the way we did it for 5x plus y is equal to 100 and x plus y is equal to 60. Then the second step is evaluate the objective function For two variables, it would be z is equal to ax plus by, and you evaluate it at each corner point. And let capital M and small m be the largest and smallest value of z at a corner point. By the way, a corner point is different from a boundary. If this is the region we have, these four are corner points, but all of these points lie on the boundaries. So we're not talking about the boundaries, we're talking only about the points at a corner. Right? So let m and m be the largest and the smallest value. Now, so basically you'll evaluate the value at each corners, you'll pick out the largest value of z among all those corners, and you'll figure out the smallest value of z among those corners. And finally, as long as the region is bounded, which will be true for most cases you see, m is the maximum value of z in the feasible region, and small m is the minimum value. Now what we'll do next is we'll look at the three most common types of linear programming problems, and then in the next video we'll do an example of each and a few other examples to get more familiar with the topic. So there are three basic types of programming problems. The first one would be manufacturing problem. In such problems, we have to basically determine the number of units of particular goods. Like the first problem we did was a manufacturing problem because we had to look at the number of tables and the number of chairs, and there would always be some constraints. So they could be like each product requires a fixed manpower, labor hour, warehouse space, etc. So we have to determine the number of units. While each product requires some different things, these would be a form of constraints. Let's say we only have a certain amount of storage space or a certain amount of labor hours, and what we have to do ultimately in order to make the maximum profit. So you would, for example, have a constraint of the form of, let's say you only have laborers working for 65 hours or something, or you only have storage space for 50 units. That would be a constraint, and you have to determine the number of units of each product in order to maximize the profit. So this would be one type of linear programming problem. We've already seen this before when we saw that the tables and chairs cost a certain amount of money, and there were two constraints: the total amount of money available and the total storage space, and we had to maximize the profit. Another type of problem could be diet problems. In these problems, we determine the amount of different kinds of nutrients which should be included in a diet while minimizing the cost of the diet such that it contains a certain minimum amount of each nutrient. So we'll need, the constraints would be, we need a minimum of this much of iron, this much of calcium, and so on. However, the thing which earlier we need to maximize the profit, now we need to minimize something, we'll need to minimize the cost of this diet. We'll see an example of this type of problem in the next video as well. And the third most common type of linear programming problem involves transportation problems. Where we determine a transportation schedule in order to find the cheapest way, so we minimize the amount of money required of transporting a product. So these are three most common types of real life problems which we encounter and we are generally able to solve by linear programming. In the next video, we'll see an example of each type of problem. We've already seen an example of the first type, and then a few other examples to be able to familiarize ourselves with this concept a little bit more. Thank you.